So then came something called driver assistance systems, which is an expanded version of active safety. It uses a lot of, as I said, same way, sensors, cameras, radars, sonars, or your ultrasonics, LIDARs came into play. As I said, your driver assistance only controls acceleration and braking, and not necessarily your, you know, where your vehicle is going, your steering. It does work very well in your, most of the weather conditions, and most of the lighting conditions may not really work well during the night because there are lack of either lighting, or you don't have the appropriate sensor for that. So yeah, so most in the example of that driver assistance is your cruise control. As I said, your rear camera tracking the based on the lane tracking, and your camera based classification and tracking, your driver monitoring system, because those are assistants, right? They're not necessarily controlling the car. They're only giving you information so you can control the car better. So this is an example of that, is that it's sensing the two cars. It's sensing the lanes where the drive lane is. So then it's actually able to tell you, okay, this is a lane, so please drive in this lane. And then these are the cars, so that you know where these are and how far they are. But advanced driver systems now has extra sensors, along with the capability that it can need not control just the acceleration braking, it controls your steering too. So this is the current, basically, where most of the companies are, the current technology, which is ADAS, or the advanced driver assistance systems. So some of these features like Super Cruise that I mentioned, which was in the ADAS domain. Then there's a lane keeping assist feature in Volvo that you can see, which is part of the ADAS domain. They're not DAS because now they're actively controlling the car, not just acceleration, but also where your car is heading. So many of these main companies that are in this domain are like Mobileye, even though they give purely camera based systems, but they do a lot of these features based on camera based systems. You have Veoneer, a Swedish company, is a tier 1 supplier. So it has its own lane keep assist features, automated emergency braking, all your advanced driver assistance systems, your DMS or driver monitoring systems. You have Delphi. Delphi also is a tier 1 supplier for all of automotive OEMs. NVIDIA, which initially was more like a component supplier, but now they were the ones who basically developed this assistant driving systems, or your in your Tesla. They're the first to do that in Tesla, a fully fledged systems that they developed on it. They have their own hardware platforms. We'll go through that a little later. So you have these players or these companies that do quite a bit of ADAS systems and provide them for OEMs. So your ADAS now just doesn't sense objects in front of it or just the lanes. It can intelligently act on it, right? It can sense not just lanes, but much more than that. Where the car is coming in, any incoming cars, barricades, where am I going? How fast am I going? So do I need to stop for a stoplight, because it can send signals, traffic signals. So it can do a lot more than what a driver assistance do, because it has to control the car. Right, you can see you are basically, I said, this shows this constantly monitoring. Unlike DAS, which is basically is limited in terms of what it gives, here there is a lot more fusion of information. There is path planning, which I'll talk about a little while. It talks about where you want to go, how fast can you go, what can you do. So knowing all of this, so then what is an autonomous car? Because we learned about what passive safety is, we learned what active safety is, we learned what a driver monitoring system is, we learned about advanced driver assistance systems. So what does autonomous cars have? What are they? So basically, autonomous cars have 4 functions or 4 areas primarily. The first area, which is sensing, basically it collects information about the environment around the car using a lot more sensors, cameras, radars, LIDARs, ultrasonics, your yared sensor, a lot more things than you know than a normal driver can do. So it has a sensing aspect. Then having all this information, it has to build what the world looks like around it, right? The perception part. Because if you were to perceive it, you have to basically, only then you can act on it. Because without knowing where you are, how the environment around you is, how can you do anything? So that is where the perception part of it is. Then comes the decision part. Now, once you know how the environment around you is, then you can say, oh, this is where I am. This is what I need to do. This is because this is where I need to go. So how do I get there, going from A to B safely without having to eat anything and in optimal way without having to go all around the place? Then once you have made the decision of how to go, then you have to actually go. That means you have to control your steering, you have to control your braking, you have to shift gears. If you're going from a stop to a start, then you go from a parking brake to your first gear. So then you have a lot more to do. So basically your entire autonomous cars can be divided into these four areas primarily. So let's go one by one. So this sensing area basically has a lot of sensors, right? It talks about sensors in the car, because you have cameras, you have so many cameras in the car right now. You have radars, you do not know where all the radars are used. And then you have LIDARs, which is a new introduction in terms of sensors, sensing systems in the car. Then you have ultrasonics, which are previously used to know if you're going to hit a wall or if you're going to hit some kind of target near the body of the car. So you have this system that basically comprises of all of these sensors, get the data from the sensors, and then provide it to the perception system or the system that perceives the environment so that it can actually know what is going on around the car. So these sensors, as I said, initially it was introduced as when you had distributed computing, you had very intelligent sensors, right? Because they did a lot of processing within them and then only sent out the process data. Now, when you have a central unit, do you need to have a processing unit at the sensor? Not necessary. You can get the raw data from the sensor, compute everything at in a central place, because an advantage to having central processing unit or in a central units is because you can then decide what data to act on, because then you don't need to act on certain data depending on what scenario you are in. So then you can choose and pick and choose which to act on. That is an advantage of having central units. That's why the sensors can now be dumb sensors which just stream data to it. Then these sensors can be connected to one or multiple of these processing units, and they have their own sensors and interfaces, right? Your sensor have to be connected to your compute units. It can be connected by any n number of interfaces, but anything that gives you a lot of interference, a lot of noise. Yeah, basically your sensors now have to have their own interfaces that connects to your processing units, because your processing units now need to get the data as fast as they can, quickly, as much as quick as they can, without any error, without any corruption, so it doesn't have to lose any information out there. And you need to power all of these sensors, right? So you are powering all these sensors also through the same interfaces. So that's another important aspect of interfaces that are in the sensors. So this is some of the sensors you can see. You have radar. This is a pretty old sensor, meaning it was introduced very early on. Then you have your cameras, which are not just new introductions, but they're used in a lot more complex operations than before. This is the newest introduction to your sensor set, which is your LIDAR, because this is you have certain advantages and disadvantages with these cameras that you can cover up with your LIDAR, because let's say it's raining pretty heavily or it's pretty foggy out there, your camera cannot see much, but your LIDAR, which basically shoots out laser beams, can actually shoot laser beams through the fog and get information through the fog. Same way the radar, if your radar now has any object in front of it, it cannot detect anything beyond it. So your LiDAR, which has different types of LiDARs, you have spinning LiDARs, other type of LiDARs, which we will see a little further, actually helps you in a lot of things, covering up all the disadvantages you may have because of these other two sensors. Now, once you have all this data, you now have to perceive it. You have to process the data. You have to learn what is the environment around it. Excuse me. How is the environment around it? Right? It needs to, because you need to act on it. It needs to build an environment of the surrounding the car. So that is where a perception data comes in. You have now fusion of data that you can do to get that layered information. So sensor fusion is a very important aspect at this point in the perception system, not just processing any individual data of sensor data. So an example of that is you see here in this picture. It has one, if a system has to build this kind of a data around it, it needs to have information of everything about the car, about the road, about the barricades, so and then the driving path. So now your car can make a decision whether is there any car in the path of its driving. Does it need to adjust because if this car may be coming into this lane, or is it going to be hitting anything? So this is basically what your perception system does, and this is how your car sees you, sees the environment around you. Yes, it sees all your objects. It sees how big the objects are, how far they are, what they are. So you can make the right amount of right decision for it. So then I said your decision. Now, what does the decision actually involve? You have your data from the sensors. Then you have the word that is built from the data. And now it has to decide where it needs to go. So it already knows it has to go from A to B. So in that path, is there any vehicles? Does it need to weave around it? How much do they have to weave? What is the speed it needs to weave at? And if it needs to avoid a certain vehicle in the path. So basically it has to plan where the car has to go, right? It basically decides the path of the car, path of the movement. Otherwise the car cannot know how it needs to go. So you can say this is the heart because it decides how the car moves. So this is the heart of your system. Heart and the brain, you can say. Your brain probably is your perception, your heart is the decision. So this is an example of your path planning or your decision making, because now you have this pedestrian walking in this direction, you have this pedestrian walking in this direction. So if you want to come and take a turn, it needs to know whether does it have a clear path, or by the time it comes to a crosswalk, does the has the pedestrian already moved away, so it can safely continue through the walking path and then take a turn. As you can see here, it has multiple paths that it decides. So it has to decide which is the best path, knowing that, okay, this is a drivable area, this is not a drivable area. You can go there because if this is an urban environment and you're in a junction where it is cobbled street, then you really need to know where you can you go, where you cannot go. So that is where your decision making comes into play. And path planning, which you have used probably in robotics and other places, actually come to use in real world in a much more complex way, because all your objects are actually moving and you are moving. So all of us is in dynamic environment. You have to make this decision with these dynamic objects in the play. So prediction plays an important role in where deciding which path to take, because it can decide what the objects are doing. So once you've decided that you're going to go in this path, now you have to act on it, which is not necessarily simple, because let's say it knows that if you go 100 meters or 200 meters, then it has to start to slow down. You can already pre-fill these brake messages or acceleration messages in the pipeline or in your in your system, that as soon as that point appears or comes, and then in the that message is actually acted on. It is something like when you're driving and are driving at 60, you need to take a turn probably 300 meters down the road. What do? You take your leg off the accelerator and just prepare yourself to brake. You don't brake, but you prepare yourself to brake by having your leg over the pedal, but not necessarily depressing it, right? So the same way, the system, knowing it's going to go a certain way, knowing that it's going in a certain speed, it has to know that it has to brake at this point for it to sufficiently slow down to do the next action. To make that happen, you actually have the brake messages being pre-filled already, and that is acted upon at that point. So what are the sensors? I talked about sensors being a lot of sensors around the car, right? In the car, inside the car, and outside the car. So you have these features in the car, right? You have your surround view feature, meaning you can see all around. You have the feature for traffic sign. You have the feature for emergency braking. You have adaptive cruise features, lane departure warning features, blind spot detection, rear collision. So you can see some of these yellow ones can be implemented by actually cameras. Some of the gray ones are implemented by your radars or even LIDARs. Then you have this GNSS, which is basically a GPS, because as I said, there's an important aspect called mapping. So it has to know where it is in the world. So you have the GPS sensor. So you have a whole bunch of sensor to basically implement all of these features. So let's look at one of the sensors one by one. So first is a camera, right? It is one of the cheapest sensors out there that you can use. Probably the next cheapest is your ultrasonics. But when you compare the performance to the cost, your cameras give you the best performance to the of sensors. So they're the most cost efficient way of introducing all these autonomous driving features, or at least is one of the primary sensors being used at this point, because you need to have information about the environment from a 360 degree, not just in the front, not just in the side. You want to stitch them all together and have a complete 360 view around the car. And for that, you have a hell lot of cameras around the car because they're cost efficient, because you can make it very cheap. You probably can get 2-3 cameras or even more for a single radar. So now instead of using multiple radars, you probably can use multiple cameras and it becomes cost effective for you. Even though there are some advantages to having a radar, but from a cost comparison perspective, your camera is one of the cheapest sensors out there that can basically enable a very high level self-driving features. You have a stereo vision camera, or not just monocular single camera. You have stereo vision. Now you can get depth too. So there are advancements in camera systems that help you get more information, right? You have all this information that you could have got from, let's say, your laptop camera, but there is some information you cannot get by using the same camera. So you have advancement like stereo vision, which allows you to get 3D information about the object, the depth as well, more accurately, directly as compared to your monocular camera. Then you have infrared. As I said, in the night probably is the most difficult part to drive. So your cameras really don't have that much of a role in the night unless you have an infrared vision camera, because you have certain companies that are doing night vision cameras just for automotive purposes. And these pick up on the heat radiations or the heat temperatures of the body of the objects and differentiate them from, are they actually humans, or is it some kind of a road object, is it some kind of a animal. So it helps you in that. So you have these cameras now that are developed far more advanced than just simple cameras that can see in the night too. So an example, I said your monocular can see only this, right? It cannot know how far this is, but it can know what it is. It cannot know how long this is, but it can only know this is a car. This is only a person, but cannot know how far this person is. But as soon as you come to stereo, now you have the depth information where you actually can get the depth information, how far these objects are, how big this object is. You can get all of the information of having this extra thing. I said your depth information, which is very vital when you want to know how far you are from the car that you're following. Because if that breaks, you need to know when to brake. You can't suddenly brake even though you're 50 meters away. Just because a car in front of you braked, you cannot brake. So you cannot have this jerky motion. Even that will be very bad in terms of systems. What I was talking about, your infrared camera, your FLIR is a company that is doing it for automotive. Actually, you'll see in the next slides where they're using automotive. So here you can see this is your normal camera image. Most of the camera, things that are you can see are illuminated by your headlights. So you should have a very big headlight that basically gets you everything, or you could have just one of these cameras and you can get that there is a person. Right? Looking at this image, you can then see, oh, there may be something here. But can you confirm the same? What is here? What is here? No, you cannot, because you do not know and you do not have the same information here. The other places where you are using the same information is when you are in shadows, especially when you're driving by tall buildings during the sunset time. So you have a long shadows on the road and you cannot see because there's diffuse sunlight coming through the buildings along with the shadow. As you can see here, you could probably guess this is an object here, not knowing what it is, but you can guess it's an object. But anything beyond this, you're not able to guess anything from this image, right? So that is where your nitrogen cameras come into use. So that is where this FLIR, which is a company that is developing this, and FLIR stands for forward looking infrared. So they actually develop these for automotive, make them, having them qualified for automotive standards, having them very rigorously tested, and they're used in, BMW and other car, companies are using it actively to get night vision systems from, implemented in their cars. Now there's a radar, is another sensor that also used very profoundly in autonomous, probably came into use well before, say, cameras came into use, because radar, which was a military technology, started to have its own advantages if used in commercial vehicles. So they started to do it. The first ever emergency braking probably was implemented, or not probably, but was implemented using radar only. But the modern day or a current year emergency braking probably has radar as well as a camera, a ray cam kind of a setup, which actually helps you to do the emergency braking. So your radar basically uses sonar philosophy, where it bursts out your sound waves and get back the reflections and basically get your measurement to the, based on the reflected waves. So that way now you're able to know there are objects out there. Then you can also get to know how far they are, but you cannot necessarily know how big they are. I mean, you can do it if you have more sensitive radar, probably have better differentiability in terms of sound, in the whatever in radar terms. So you could do little more, but your regular radars or in general radars can only give you how far they are. They're not necessarily giving you what they are. So it has its own uses. If you don't want to know what it is, you can happily use radar and implement many things. But the only thing is it's narrow field, right? It's not as wide. You can have a 360 camera. You could have a fisheye camera that looks a lot more than 180, but you cannot have a radar that does that, because then your radar actually has a lot of confusion, a lot of stray reflections out there. So your radar actually is narrow field, so it does need multiple units in the front to just cover the whole front portion of the car. Along the sides you probably have 3 radars. In the rear you have another 3 radars. So you have to cover 360. So you need more radars. But with a camera you could cover it much faster with less number of sensors. So you have this advantage of one sensor over the other. But if you use a monocular camera, you can never know how far the objects are. You can only know there is an object. So now your radar still has to be used. So this is an example of when you visualize your radar detections. It shows how these detections are visualized, and the green things are basically objects with certain confidence, and these are reflections which can turn into possible objects in the future, or they can be stray or no detections altogether. So this is a visualization of how a radar data looks like. Now the newest sensor in the domain of autonomous vehicles, because probably 2015, 2016 onwards is when people started to talk about LIDAR more actively to be used in a commercial vehicle, because LIDAR was used before. It's a very expensive sensor. Even today, it's the most expensive sensor in the car. It is not necessarily the cheapest, it's the most expensive one. and they were not necessarily ready in terms of to be used in all type of weather conditions. So if it gets soaked in the rain, many of the lidars would actually go bust. It would stop working. Unlike some of the other sensors, like camera can get soaked in the rain and probably has more chances of working after getting soaked. Your radars are also built certain way that it can get soaked and still work, but lidars were not. But nowadays there are companies like Velodyne and other companies that are actually building radars purposefully and for the sake of using in automotive only and not any other application. So LiDAR works the same way as radar, where it is using the technology of ranging, where it shoots out laser beams and then gets the reflections back and measures the uh, at what speed it came back, so it knows the how far the object is. This LiDAR actually gives you data points, right? They give you data, your point clouds. They don't give you objects by itself, because it cannot get reflected of the whole object. It can only get reflected from every point on the object. But it can also work in many weather conditions where your camera doesn't work. So this LiDAR is very sensitive. It is very accurate when it's trying to get an object, right? Because you can have multiple scan lines, because you can shoot light rays or lasers in different lines, So you have 16 line, 32 line, 64, 128 probably is one of the highest right now with the high level of precision. So you have 128 beams of ray, or rather 128 lines of light rays that have been shot from the LiDAR, and the reflected light is being reconstructed into a point cloud. So this gives you a very good granularity where you can actually now detect single drops of rain at times. So if you do a little more processing, if you have a higher beam LiDAR, you can actually even do a lot more precise, triangulation to the objects. So to do 3D mapping, LiDAR now has become very useful, or the crux of the entire mapping relies on LiDAR with camera to actually get what is around the car more accurately, because it can give you the depth information and it can use the structure of the object. So knowing the structure of the object, you can do some kind of object detection on it and get what the object is. So a LiDAR can do the work of both radar and camera combined. So this, when it start to become cheaper, probably will find more use and wider use in automotive. So this is one of the visualization of the point cloud. As you can see here, it's almost like a 3D scan. I mean, there's a reason why you have the shadow is because you have light rays coming in through, and they're not basically, going past the person. So you have a shadow of it. So you can get the shadow of the person. This is how accurate, or how good the LiDAR mapping is. So LiDAR now has a lot of good use in automotive industry. It has three components: the scanner, which is basically scanning for the entire line. Then you have the laser itself, shooting out lasers. Then you have the GPS, because most of your LiDARs comes with the positioning system. So it knows at what geolocation it has taken the scan. So the photo detector here is very critical, because if you do not have a good enough, or if you do not filter out some of these stray, reflections back, you may have ghost objects. If you do not have good optics, or the optics is damaged when it's getting the light rays back, you can actually get deviated within the optics and then give you a very wrong information about where the object is. So these parts of the laser LiDAR are actually sensitive, but also they play a vital role. So hence LiDAR now has, still is more, how do I say, the conservative way. Conservative companies do not go for LiDAR because they're more expensive, not necessarily work in very rough conditions. At times it can go wrong. It cannot work in many of the weather conditions, so you have to have some kind of encasing extra for that. So companies have developed that, but that only adds to the extra cost of the LiDAR. So yeah, so you have airborne LiDARs and terrestrial LiDARs. Right? We are using terrestrial LiDARs primarily in automotive, nothing more, because they can be used in any moving vehicle or tripods. Your airborne LiDARs are, they work in a different way. The optics are different. So they're not necessarily useful as compared to a terrestrial LiDAR. So this is another part where this scene out there actually now has the LiDAR scanned by the LiDAR, probably by a 32 beam LiDAR from a Velodyne. So this is where it gets the information, very accurate information about your environment.